So in this video we're going to look at one last example of partial fraction decomposition, and we're going to do the case where we have repeated quadratic factors in the denominator. We're not going to take this all the way through to completion, just enough to get us to see what we need to do. So when I look at this, I want to recognize that it's already in a factored form. The x squared plus 3 can't be factored further over the real numbers. And we can tell that because x squared plus 3, if we try setting it equal to 0, we get x squared equals negative 3. And when we take the square root of both sides, we get a complex root. We get two complex roots, which means it factors over the complex numbers, but it doesn't factor over the real numbers. So over the reals, this is irreducible. So we'd step over here, and we'd have 2x cubed plus 6x minus 3 all over x squared plus 3 all squared. So this is a repeated quadratic factor. The quadratic factor is x squared plus 3, and it's repeated twice. So if this can be separated into the sum of two integrals, they're going to look like this. There'll be something over x squared plus 3 plus something over x squared plus 3 squared. So remember this, the squaring on here, the exponent m that you get based on video 1, if this had been a 4 instead of a 2, we would need to keep going. We would need to put plus something over x squared plus 3 cubed, and then we would need to go plus something over x squared plus 3 to the 4th. So starting at an exponent of 1, you have to walk all the way up with every possible integer exponent that you can get up to the max size of the exponent right there. That was loud. So we don't have a 4, so this is only squared, so we only need to add on the 2 extra terms. And then we look inside of here, we see we have a quadratic, so the numerator has to be a guess of 1 degree lower than the denominator. So we're going to guess ax plus b. We're going to guess that the numerator is linear. And here it's still the x squared plus 3 is the core term, so we're going to guess another linear expression, cx plus d. And then we need to think about, well, if we got that common denominator, which is x squared plus 3 squared, how would we need to modify these two terms? And what we can see is we would need to multiply this term right here by x squared plus 3 over x squared plus 3. So in the numerator we would wind up with an ax plus b times x squared plus 3. And this guy, he already has the common denominator, so plus we wouldn't need to make any modifications to the cx plus d term. So we'd wind up with this. And then what we want to recognize is that we have the same denominator on both sides. So for this rational expression to be the same as this rational expression, we need the numerators to match. So what we need is 2x cubed plus 6x minus 3 to be equal to the numerator over here, the ax plus b times x squared plus 3 plus cx plus d. And we're going to take an approach to this that's different than we did in the previous few videos. There aren't a lot of values for x to plug in and get things to cancel. We could plug in x equal to 0 and get an a and a c to cancel, and we would get an equation that had a b and a d in it. But there's 4 unknowns, a, b, c, and d, which means we need 4 equations if we take the approach that we've been taking. So because there's only one value of x that gets anything to cancel, what we'll do instead is expand everything out and group like terms and then equate common coefficients. So let's look at how that plays out. We do ax times x squared is ax cubed plus ax times 3 will be 3ax plus b times x squared is bx squared plus we'll get b times 3 is 3b And then that's everything from multiplying out these two binomials, and we're still left with the plus cx plus d. And now we want to group like terms. So there is only one cubic term, that's the ax cubed. There's only one squared term, that's the bx squared. Plus, there are two terms that have a linear x on them, right here and here. So if we factor the x off of those two terms, we would wind up with 3 times a plus c times x, factoring the x off of those. Plus, we have 3b plus d as our constant terms, the only terms that don't have any x on them other than x to the 0. And then what we do is we look at the right hand side and we equate coefficients. So here's the only cubic term, here's the cubic term on the other side, and for the left side to equal the right side, what we can notice is that a will need to be equal to 2. It's the only choice that we have for a, so a must be equal to 2. Similarly, here's a bx squared, and I see there's no x squared terms on the left hand side, which forces b to be equal to 0. And then here I have 3a plus c. 3a plus c is the coefficient on the x term, or the linear term. So it's going to need to be equal to 6. 3a plus c needs to be equal to 6. And then here the constant term is 3b plus d. 3b plus d. And the constant term over here is a minus 3, so this will need to be equal to negative 3. So we've got 4 unknowns and 4 equations, and then these two, we already know what a and b need to be. We can start plugging these values for a and b into the other two equations. So a is equal to 2, says 3 times 2 plus c needs to equal 6. 6 plus c needs to equal 6. Subtract both 6 from both sides. We see c has to be 0. And over here, b has to be equal to 0. So 3 times 0 is 0 plus d equals negative 3. d must be negative 3. So then you're ready to rewrite your integral. You say, here's the integral I'm starting with. I have a 2x cubed plus 6x minus 3 over an x squared plus 3 quantity squared dx. And this integral can be rewritten as the sum of two integrals. The first one's going to be have an x squared plus 3 in the denominator, plus the other one's going to have an x squared plus 3 quantity squared in the denominator, and this will be a dx. And here a is 2, so we'll get 2x plus b, but b is 0, so we just get 2x sitting here. Plus, we step over here, we see down here c is 0, so we get 0 times x is 0 plus d, but d is just negative 3. So here's the integral that we get. And I'm kind of going to leave this here. We would need to evaluate this integral. What we want to notice is that this first one would be easy. This first one would be easy. This would be a natural logarithm because it has the form crap prime over crap. The derivative of the denominator, x squared plus 3, is 2x, showing up in the numerator. So this would just be a natural log of x squared plus 3. But to get this guy right here, he's still a little bit difficult. And what you can see is that you're going to need to try trigonometric substitution on that one. You're going to need to do trigonometric substitution where you set up your right triangle, you label your angle theta, and then you recognize that you have the sum of two squares. So one leg will be x and the other leg will be the square root of 3, because 3 is equal to the square root of 3 squared. And the hypotenuse of this baby is going to be the square root of x squared plus 3. So we would need to set up a trigonometric substitution and try to knock this out. Or the other option is to look in a table of integrals and see if this integral pattern shows up in a table of integrals. So still work to do, but you're in better shape than you were to start with. And even if you can only evaluate one of the two integrals, say this one, you're in better shape because now you have a simpler integral if you need to do an approximation technique.